Are you tired of composite numbers? Don't you wish everything was divisible only by itself in 1? Wouldn't life just be simpler if all numbers were prime?
Hi, I'm Mac May, and I'm here today to bring you an exciting opportunity to increase the number of prime factors in your life. Our engineers have been working around the clock to bring you this algorithm. Believe it or not, it will give you the prime factor of any natural number. It's true. Let's go over exactly how it works. This first while section up here takes care of those pesky even numbers. Don't you hate even numbers? Except for the 2, they're never prime. But 2 is alright, and churning it out is exactly what this section does best. By the time any number gets past this part, not only will you have the exact number of 2's that are factors of your original number, but it will be odd until you are done factoring. And believe me, I know odd. But that's just the start. Now we get to the real meat of the algorithm. We start off by establishing that I is 3, and then we take our number out for a spin. As long as I is less than or equal to the square root of whatever number made it out of that first loop, we stick around to check. Why? I'm glad you asked. We're looking for any 2 numbers that will multiply into what's currently left of our number. By definition, the square of n times the square of n will always equal n, meaning that if either one of them is higher than that, the other must have already been lower. So, once you've checked that high, you checked as high as you need to go. Now, where were we? Right. Here we are in the main loop. We start with 3, the lowest prime number above 2, which we took care of in the previous loop. And obviously, any number has an infinite number of 1's in its factor, so let's just ignore that. So we check 3, and here, we remove it from our number as many times as it will go. Once 3 doesn't come out cleanly anymore, let's advance I to the next odd number, and try again. Why only odd ones, you say? Well, because we know evens can't be prime, and we're only interested in prime factors. But wait! Not all odds are prime. What happens if we try to divide by 15 and it works? We'll end up with a non-prime factor. As it turns out, you don't have to worry. None of those will work. Yes, with a big enough number, our algorithm will eventually try 15, but it will never factor out. Why? Because any composite odd number is made up of prime factors, and by that point, we'll already have tried them all. So 15 will never work, because by the time we get to 15, our number will have had all the 3's and 5's taken out of it earlier in the algorithm. There's no point in writing code to skip over non-prime even numbers, since our algorithm will just check them once and skip them on its way, on its own. Anyway, back to our algorithm. At this point, all the hard work is done. The number will keep rinsing through this statement, churning out as many copies of each prime factor as it can handle, until finally we're checking its own square root. And if that doesn't work, guess what? The number itself is prime! The last little itty-bitty bit here at the end takes care of that scenario for us, printing out the final number once we've run all the rest of the prime factors out of it. Now, of course, you're thinking, that's too good to be true. But wait, we can show you. This isn't just a theoretical idea. It really works. Let's take it for the spin. Start off with an easy one. 7. We check the first while, but 7 mod 2 isn't 0, so we skip it. Next, let's check the second loop. The square root of 7 is between 2 and 3, so already that's less than 3, so we skip this loop too. Then the final line sends the 7 straight to our printout. Of course, I know what you're thinking. Anyone could do that. It started prime. But not every number does. Let's try something we can really get our teeth into. 980. What happens here in the first loop? Well, mod 2 is 0, so we print out a 2 and divide our n by 2, giving us 490. Mod 2 is still 0, so let's print out another 2, and now the newest n is 245. Mod is finally 1, so we leave this loop. We've squeezed all the 2's we can out of our n, so we don't have to worry about coming back. Nothing else we divide is ever going to give us another even number. Now, the main loop. Our square root is over 15, so we'll go ahead and check 3. However, mod 3 isn't 0, so we're going to skip here and advance to the next odd number, 5. This time, mod 5 is 0, so let's print out that 5 and divide it from our n, giving us 49. Mod 5 isn't 0 anymore, so we break back out to the bigger loop, advancing to 7. Now this time, the square root actually is equal to I, which means we still do the loop. Mod 7 is 0, so we print out 1 7 and divide n by 7, giving us 7. Mod 7 is still 0, so we print out and divide again. Now 1 mod 7 isn't 0, so we break out, advance I again, and check. Now the square root of 1 is 1, and 9 is greater, so we're done. Down here, n isn't greater than 1, so we skip that. And look, our factors, nothing but primes. Prime, best by definition. As if that wasn't enough, the factors are even sorted. Now how much would you pay? Alright, I know what you're thinking. An algorithm this nice, its runtime must be through the roof. But it isn't. You can get this whole thing for the low, big O notation of log n or the square root of n. And if you think that's nuts, get a load of this. Log n is already big O the square root of n. So your runtime is really just that, the square root of n. And that's our final offer. How can we afford such low runtimes, you ask? It's easy. Our first loop here runs in log n. Worst case scenario, the entire number has nothing but 2 as factors, so we run through that. Each time you do factor it, you divide by half, so the number of calculations is just whatever the exponent 2 would have been raised to get the number. Well, that's just a fancy way of saying log n. As for the second part, we've already gone over why we only need to check every number up to the square root of n, but we don't even need to check all of those. Remember, there are no even primes above 2, so our worst case is only half of that. Still, for things like big O, we drop coefficients, so it's basically just big O of the square root of n. Hurry up and get on our website to order your prime factorization algorithm while this low running time lasts. Our bots are standing by to automate your orders. What are you waiting for?
Algorithm not valid in California, Canada, or some parts of the moon. Must have at least a paper and pencil to run this algorithm. Your runtime may be faster than what is shown here. No refunds of prime factors available. Only works on natural numbers. Does not work on imaginary numbers. This algorithm has never been seen in the same room as Clark Kent, but we are assured this is just a coincidence. I just made this disclaimer up, and it doesn't actually mean anything. It has no legal standing whatsoever.